big three, really your millimeters of mercury, your torr, and your atmospheres. Remember that 1 atmosphere is equal to 760 torr, and that is equal to 760 millimeters of mercury. The relationship between millimeters of mercury and torr is a 1-to-1 relationship. So that 760 number is the number that we use to sort of convert between those two units. Number stays the same, just the units change. We talked about some gas laws. We had our friend Boyle, which is P1 V1 equals P2 V2. This is at constant temperature. And what we saw was as the pressure goes up, the volume goes down, and vice versa. Pressure goes down, volume will go up. We also talked about Charles' law. V1 T1 equals V2 over T2. This is at constant pressure. And as we talked about, what happens in this situation is as the temperature increases, the volume will also increase to allow the number of collisions to remain the same and thus keep our pressure constant. And vice versa, as the temperature decreases, the volume will also decrease, again, to maintain that constant pressure. So again, in a Charles law situation here, we have the volume adjusting to allow the pressure to remain constant. Just like every gas law, temperature always needs to be in Kelvin. So definitely it's a safe bet. You got to go Kelvin on it. We had Guy Lusik's law, and that's a little P1 over T1 equals P2 over T2. In this case, this is constant volume. So in this case, we're not going to get that adjustment of the volume like we do in Charles' law. And that means that when you do increase the temperature, you will see pretty much a increase in the pressure because we'll have more collisions. As we decrease the temperature, we'll see a decrease in the pressure that's going on there. Lastly, here we got to, I think, Avogadro and our friend there. And Avogadro's law is V1 over N1 equals V2 over N2. This is at two types of conditions. This is constant pressure and temperature. And one of the things that we saw with Avogadro's law was that you can really do some stoichiometry, just like you do sort of the mole-to-mole relationship. Obviously, N is moles here. T still has to be in Kelvin on that guy as well. But as the volume increases, so does the moles. And again, like we saw, if you have sort of a gas sort of reaction happening and you want to do a little bit of some stoichiometry, and it's at constant pressure and temperature, you could do like a 3 liters of A would equal 1 liter of B. So you could kind of do like a volume to volume relationship, like you do a mole to mole relationship. And it will allow you to sort of, again, like I said, sort of skip over maybe incorporating a gas law into your calculation by being able to do that. Any questions on any of that there? So kind of continue on here, reviewing some of the relationships we just talked about again. As you can see there, smaller volume, we're going to have an increased pressure with Boyle's law. Again, they just don't have as far to fly around, going to increase the collisions. When we increase the volume, again, that's going to lower the pressure as it's a little further for them to fly around in, and going to decrease the pressure. We saw our Charles law here again. Our volume will increase to keep the pressure from going sort of crazy. But in this case, a lower temperature, we will have less lower pressure in that case. And again, it's that volume that will adjust to allow that pressure to remain constant. And our Charles law sort of idea with our pressure and higher temperatures. Again, if our volume is fixed like it is here, we don't get that adjustment and we will see an increase in the pressure as opposed to up here where we do see the volume adjust and that allows pressure to remain constant. And our Avogadro's law, which includes the moles here, again, as the volume increases, so does the moles as well. So putting all of those guys together, all those sort of laws gives us sort of the granddaddy of them all here, which is the ideal gas law, which is PV equals nRT. The ideal gas law is different than all the other ones, as this is kind of like a one and done situation. So there's kind of no two pressures, two volumes, just kind of one of everything. It is also the most restrictive in terms of units. So if you are using the ideal gas law, your pressure does need to be in atmospheres. Your volume does need to be in units of liters. Your moles should hopefully be moles. And obviously here your temperature should be Kelvin. And the reason for all that is R. R is a gas constant. And R is a value that you sort of always have available to you. Once again, they very rarely will even mention R or anything about it in a problem. It has a value of 0.08206 liters times atmosphere, Kelvin times mole. Some books and people nowadays kind of round a little bit on this to 0.0821, which is okay as well. And the good news is, if you're not sure what everybody else's units have to be in the ideal gas law, pretty much this will tell you what everybody else's units need to be in, so everything cancels out correctly. What is an ideal gas? An ideal gas is really a gas that under normal sort of conditions of temperature and pressure will behave what they consider ideally. And basically what that means is there's kind of two main things that makes something an ideal gas. One main thing is the volume of the gas is not all that important and sort of negligible compared to the container it is in, the container sort of volume. So if you read through a lot of sort of gas problems, they oftentimes will not talk about the volume of the gas itself. They'll talk about the volume of the container it's in, and that's really more important. Again, the idea here is we feel the gas will fill the volume of that container uniformly all the way through it. The second thing that really makes something an ideal gas is under ideal conditions, there's really no attractive or repulsive forces between gas molecules. So what that means is you could have in a container a bunch of gas molecules flying around, and under ideal sort of circumstances, which is most of the time what we sort of think of, the gas A will have no effect on gas B, and gas B will have no interaction with gas C. It is almost like they're in there by themselves. So that allows us to do certain calculations as well. So those are the two main things that make something an ideal gas. Really, the volume of the gas is negligible compared to the volume of the container. And if you have a bunch of gas molecules all in the same container, there really will be no interaction between those gas molecules. And we'll talk about a situation where you do see interaction a little bit at the end of this chapter when we talk about real gases or non-ideal gases. But in an ideal gas situation, again, it's almost like each one's in there individually. Nobody's interacting under ideal situations. The ideal gas law is sort of like a universal gas law as well. It works for pretty much all gases and under most conditions and stuff like that. So it's kind of a good little one to know. A couple other important sort of relationships in terms of the ideal gas law and gas in general is STP. When we see STP, STP stands for standard temperature and pressure. And when they give you like a STP in a problem or say find the volume at STP, they're actually giving you two values. The temperature value that you would use is your 273 Kelvin. The pressure value would be 1 atmosphere. So that is basically STP conditions. So again, much like R, which is not usually mentioned in the problem, if they mention STP, they don't usually tell you, hey, those are the two values you should use. Now, If you want to use the ideal gas law under STP conditions, you can. You could also use it under non-STP conditions as well. But if you happen to be at STP conditions, and that obviously would mean these two conditions here, an atmosphere for pressure and 273 for the temperature, there is a really nice relationship that 1 mole of any gas will equal 22.414 liters. So this is like a conversion factor that will allow you to maybe not have to use the ideal gas law. And you could kind of use this as sort of bypass the ideal gas law. You can only use it though if you're at STP. So you can only use if you're at STP. So if you're not at STP, you should not use that. If you're afraid you're going to, again, maybe use it incorrectly, don't even worry about it and just put everything into the ideal gas law. It all works out fine the same way. So if you're worried about using it incorrectly. By the way, that is how we get our R value. If you put everything under STP conditions into the ideal gas law and solve for R. So that would be 1 atmosphere for pressure, 22.4 for the volume, 1 mole and 273. That is where our gas constant comes from, our 0.08206 version of it. All right, so I want you to try one here. Calculate the pressure exerted by 1.82 moles of SF6 gas in a vessel that is okay, so just like last time, as we talked about, it's a really good idea just to kind of pull out the information, and oftentimes it'll point you in sort of the right direction. So clearly, we're looking for a pressure. We have moles, which is 1.82. We have a volume, which is 5.43 liters. And we got a temperature there of 69.5 degrees Celsius. So clearly here, when we look at it, we really only have one of everything. And the only gas law that we saw that had basically one of everything is the ideal gas law. And obviously here, if we're going to use the ideal gas law, we do want to make sure that everything's in the proper units. So here we do have moles, so that's good. We do have liters. Like normal here, we do need to convert our temperature into Kelvin. So we'll add a 273 to it. Gets us 342.5 Kelvin. And now I think we got everything we need. So a little P equals nRT. In this case, we are solving for pressure. It's not really a fraction, but when you move something to the other side, it ends up on the opposite location. So we'll divide by the V there and gets us P is equal nRT divided by V. Putting in our numbers here, 1.82 moles. 0.08206 liters atmosphere Kelvin mole. Remember, that is R, which never is usually mentioned in the problem, but it is something that you always have available to you. Divided by our temperature, which was 342.5 Kelvin, all divided by our volume of 5.43 liters. Moles will cancel, Kelvin will cancel, liters will cancel. Gonna leave us atmospheres as our only answer unit left. And if we do that there, we will end up with about 9.42 atmospheres in this case. Questions on that one there. Now, not necessarily in this problem, but I would say also common conversions, grams to moles, a lot of times you need to do. So again, that is the molar mass. And also volume, milliliters to liters is a common conversion that you use. 1,000 milliliters equals 1 liter. So again, those are not that we had to use in this particular problem, but typically a lot of times you do have to use it. Any questions? All right, then why don't you try this one? What is the volume in liters of 49.8 grams of HCl at STP? Hydrogen, again, 1.008, and Cl, 35. Okay, so let's take a look again. We're looking for a volume, and we have 49.8 grams of HCl. We definitely could get to moles of that, so we do kind of have N. We have STP, which means my temperature is 273, and my pressure there should be 1 atmosphere. And we always have R, which is 0.08206 liters atmosphere Kelvin mole. So if we think about the ideal gas law, PV equals nRT here, we're going to be looking for volume. We do have pretty much everything else here. We do need to obviously convert our grams into moles. So we'll go 49.8 grams of HCl. We'll use the molar mass, which is basically just adding those two numbers together. So 3545 plus 1.008. Going to get you about 36.46 grams per mole. We'll go 49.8 divided by 3646 and get us about 1.366 moles of HCl. So now we do have the moles, our temperatures in Kelvin, everybody else is good. So if we solve for volume, nRT over P, putting in our moles 1.366, 0.08206, which is our R. Our temperature 273 Kelvin, all divided by our pressure here of 1 atmosphere. There it is. Atmospheres will cancel, Kelvin will cancel, moles will cancel. Going to leave us liters as our answer, and we will end up with, looks like, 273, basically 30.6 liters in this particular case. Any questions on that there? Now, yeah, it's probably just some rounding somewhere around there. I use actually the whole number. I didn't use the rounded number when I did the calculation. Now, could we have solved it a different way? And the answer is yeah, we could have, because we actually were at STP conditions. And because we were at STP conditions, we could use that at STP. 1 mole of any gas is 22.414 liters, which means we could have just took our moles there, 1.366 moles of HCl, and use that conversion. 1 mole is 22.414 liters. The moles will cancel, and it'll get you back that way as well. So again, you could have shortcutted it and not have to use the ideal gas law. And the only reason we could do that is it is at STP conditions. Once again, if it was not at STP conditions, you could not use that conversion. But as you can also see, even if you don't want to worry about it or remember it or not sure, always you could go into the ideal gas law under any conditions and just put the numbers in, and you should be fine. Question on that there. Okay. So let's talk a little bit about some changes that can occur in all three variables. And if we take the ideal gas law and basically solve it for R, which is a constant, that means that these two numbers equal each other. That means we could actually set these two guys equal to each other, which gives us down here. And in a lot of cases, the moles will remain constant as 1. And that gets us to what is sometimes referred to as the combined gas law, which is P1 V1 over T1 is equal to P2 V2 over T2. Here again, temperature does need to be in Kelvin. Pressures or whatever you like it to be, as long as they're the same on both sides, and same thing with the volume as well. So this is one where we can see all three variables sort of change as well. Now, obviously, we could plug and chug into this equation, and rearranging again can be difficult for some people. So again, just opposite locations if you go across the equal sign. But if you had to invest your time maybe in remembering 1 or 2 gas laws, I would probably choose this one, and this one is a good one to remember. So, for example, if you take P1, V1, and if you want to remember it with the moles in there, you can. N1 and T1 equals P2, V2, N2, T2. So why would this be a really good one to remember? It's a good one to remember because, frankly, you could pretty much get all the other gas laws we talked about from this one. So, for example, if you come across a problem and it does not mention anything about moles, does not mention anything about temperature, or you're told they're held constant, all you have to do is just scratch those out on both sides. And there you go. You are now left with our friend Boyle's law. Right. If you take this sort of combined gas law here, and you come across a problem where it tells you you're holding pressure and constant and moles constant, or there's no mention of moles. You just, scratch out pressure and moles on both sides. And now there you go. There is Charles' law right there. If you take the combined gas law here and you come across a problem where they're telling you they're going to hold volume constant, and maybe there is no mention of moles or grams. Just scratch out volume and moles on both sides. And there is Guy Lussick's law. Maybe you take the combined gas law and you come across a problem and you're like, well, it tells you that pressure and temperature is held constant. You scratch those out on both sides. And there is Avogadro's law. Right? So from this one gas law, you pretty much can get every other gas law that you would need. So if you want to invest the time, I would probably invest the time in remembering the combined gas law, maybe with the moles in it. And again, basically all you gotta do is scratch out whatever is not mentioned, whatever's held constant. What you're left with is probably the right formula to use to solve for your problem. And your friend, the ideal gas law, which by the way is pretty much where this comes from, two of those together as well. So if you remember these two, pretty much have every gas law that you need pretty much right there on your paper, and you could get to them really, really easily. Any questions on how to do that there? Yeah. Okay. So let's take a look at one here, a little rearranging. Consider a sample of oxygen gas at 27 degrees Celsius. The volume is 9.55 liters, pressure 2.97 atmospheres. It goes to 8.25 atmospheres and heated to 125. What is the new volume of the gas? So take a moment there. All right, so again, we're just going to kind of pull out the information. I got a temperature that is 27 degrees Celsius. I got a volume that's 9.55 liters and a pressure there of 2.97. Got myself another pressure of 8.25. Got me another temperature there of 125 degrees Celsius, and we were looking for a volume. So again, it should kind of really point you to the combined gas law. And once again, if you maybe remembered this one, not a big deal. You just, again, would scratch off what's not there. And there's nothing about grams or moles, so you can just scratch it off, and there it is. We do obviously need to do some conversions here for our temperatures. So we're going to add 273 to each of those there. And that's going to get us our temperatures 300 and 398 Kelvin. Our pressure is okay. They are both in atmospheres. Again, they do have to be the same unit. If they weren't, you would have to fix them. So in this case, you could call these guys ones as long as you keep the numbers that go together, and these guys could be twos. So we are looking to solve for V2. So once again, if you just want to quickly rearrange, basically, if you move across the equal sign, they end up in the opposite locations. So we would have to move our T2 to the top and our P2 to the bottom, basically. And that would get us that V2 is equal to P1 V1 T2 divided by T1 P2. We obviously want to make sure we put our right numbers in the right spot here. So 2.97 atmospheres, our 9.55 liters, our second temperature, 398, divided by our first temperature, 300, and our second pressure, 8.25. Atmospheres will cancel, Kelvin will cancel. Gonna leave us our answer here in liters, and 2.97 times 9.55 times 398 divided by 300 equals divided by 8.25 equals, and that's going to give us a volume here of 4.56 liters in this case. Any questions on that one there? So again, if rearranging equations is a little difficult for you, you should take a moment, make sure you know how to rearrange them correctly so that you do solve for the right thing and you're not inversing some numbers where they shouldn't be. Any questions on the combined gas law? Handy dandy one. Yes, that one. All right. The next thing we're going to talk about is calculating density and the molar mass for gases. So you could calculate the density of a gas. You can also calculate the molar mass of a gas. Typically speaking, density calculations are for gases are, as we talked about earlier, grams per liters, typically the units that we kind of shoot for. Molar mass, as we know, molar mass is grams per mole. So that is sort of what we're shooting for here. So the density is mass over volume, which would equal the pressure times the molar mass times the R and the T. And those are our ideal gas law, guys. The P, R, and T needs to be an atmosphere. R is still our same R, our 0.08206 number. And obviously our T there is temperature in Kelvin, obviously here as well. And that should be in atmospheres as well. You can calculate the molar mass here by taking the density that's in grams per liter times it by RT over P. Now, look, do you really want to remember a couple more formulas? Probably not. So, honestly, both of these, and you can solve for both of these problems by just rolling with your friend there, the ideal gas law. So, you could do the ideal gas law, a lot of times some dimensional analysis, and just look at the units. And you can pretty much do these formulas without having to memorize them. Or if you want to memorize them, you could just memorize them and roll through them. But again, it might be easier just to kind of think about the units of where you need to end up and use the ideal gas law. So let's take a look at a couple here. Why don't you try one here and see what you come up with? We're looking for the molar mass here of this gas that is 2.1 liters and 4.65 grams and has a pressure of 1 atmosphere and a temperature of 27 degrees Celsius. Take a moment, see what you come up with. Just use the ideal gas law because I remember that one for sure. I'm going to pull out my information here, and I do have a volume that is 2.1 liters. I got me 4.65 grams. I got a pressure here that is 1 atmosphere. Got a temperature just 27 degrees Celsius. And I'm looking for the molar mass. And I know that the units of molar mass are grams per mole. So right off the bat, I don't have to figure out too much. There is the grams, right? So the rest of it, I got P, V, and T. I always have R. That's looking a lot like the ideal gas law. That might be helpful here, as I mentioned. And if I take a look at the ideal gas law, I got V, I got T, I have R, and I have P. Lo and behold, the only thing I'm missing is N. And that would be obviously the bottom part here to give me the moles that I need. So I'm just going to solve the ideal gas law here for N, which would be PV over RT. Really, the only thing we got to worry about here is our temperature. So we'll add a 273, get us to Kelvin. Now we could put in our pressure, which was 1 atmosphere, our volume, which was 2.1 liters, our R 0.08206 liters atmosphere Kelvin mole, and our temperature 300 Kelvin. Liters are going to cancel, atmospheres cancel, Kelvin cancel, leaves us moles that are left. And that's going to get us 2.1 divided by 0.08206 divided by 300. Looks like we'll end up with 0.08530, we'll call it. So now I got the moles, I got the grams. That is both of the things that I need for my molar mass. So my molar mass here is going to be the grams, so 4.65 grams divided by my moles here. And obviously here, none of those units are going to cancel, so 4.65 divided by my answer going to get me about a 54.5 grams per mole as my molar mass in this case. So as you can see, it's really just the ideal gas law, and that's pretty much this part of it here, the ideal gas law, and basically the density. So once again, you don't necessarily have to remember those formulas. You just kind of think about the units that you need and the ideal gas law. Any questions on that one there? All right, then let's try another one here. Let's take a look at this. What is the density in grams per liter of O2 gas that at 778 torr and 27.5 degrees Celsius? Given to us a 778 torr. We do have a temperature given to us 27.5 degrees Celsius. Clearly, we always want to probably convert our temperature into Kelvin. Gives us 300.5 Kelvin. Since I mentioned earlier, I'm probably going to use the ideal gas law. I'm going to convert this into atmospheres as well. And we'll do 778 divided by 760. Going to get us a 1.024 atmospheres in this case. All right, so I'm going to use the ideal gas law, which you could definitely use here for density as well. You obviously could go with the formula we saw on the previous slide as well, but just in case you can't remember it, we could think about a couple of things here. First off, I do have pressure, I do have temperature, I also do have R as well, always available to me. That's good. I am missing these two guys, so I could rearrange the ideal gas law and actually solve for N divided by V. And if I do so, I'm going to bring this guy this way and bring these two back the other way. And that'll give me P over RT is equal to N over V. Now, if I do that, N is moles, right? And V is liters. Dare I say that is the molarity of my gas right there, right? If I solve for N over V, that is molarity. And that's okay because that will end me at moles per liter, and I want to get to grams per liter. So really all I have to do to convert that is molar mass, right? To go from moles to grams here. And I can use the molar mass to sort of finish it. So again, I could kind of use the ideal gas law here a little creatively. N over V gives me P over RT. If we put that in there, our pressure was 1.024 atmospheres. Our R 0.08206 liters atmosphere Kelvin mole. And our temperature of 300.5 Kelvin. Once again, here, atmosphere is going to cancel, Kelvin going to cancel. When you divide the bottom, the moles go to the top, liters go to the bottom. And we will end up with, at this point, by punching the right numbers might be a better move. We will end up with 0.04151 moles per liter here of O2. Like I said before, the bottom part's good because we do want liters. We really now just have a mole to gram conversion here. We also want to remember that O2 is diatomic. Yeah, so that's going to be 32 grams per mole, not 16, right? So if we do that there, we want the moles to cancel, opposite location here, and 32 grams up on top. Moles will cancel, and now we're going to be left with grams per liter. And we'll times that by 32, and we'll get something like 1.33 grams per liter in this case. So once again, just to show you, you can kind of get to it through the ideal gas law. And again, you don't have to necessarily remember both of those formulas, or you can just remember those formulas and pop the numbers in to those formulas. Question on that there. And by the way, in case you ever need to solve for the molarity of your gas, that would be how you would do it there. N over V would solve for the molarity of your gas. All right. That's sometimes how they do like kinetics experiments, because all they have to really measure is the pressure change, and they can do kinetics type of experiments for gases. All right, the next thing we're going to talk about is everybody's favorite thing, stoichiometry, because we haven't seen enough of that yet. So this is gas version of stoichiometry. And just like all the other versions of stoichiometry, it's the same move. So you're still going to pretty much roll with your balanced equation. You're going to still convert to moles. Remember, as we've talked about, you always want to make sure, do you or do you not have a limiting reagent type situation? If you do, then obviously you need to go limiting reagent route. If you don't, then it's just a basic problem. We're going to do our mole to mole relationship here. And lastly, our moles to some other unit. So what is the difference here with gas stoichiometry? The difference is at some point you are going to use probably the ideal gas law. You're going to probably use the ideal gas law somewhere, like PV equals nRT. If you use it up here, you most likely would be solving for N, which would be PV over RT. But very commonly, you will a lot of times use it at the end here and maybe solve for something like volume. And you obviously would be given the other pieces of information. So I would say very commonly at the end, you'll use the ideal gas law, but you could use it both places or just the second place as well. Any questions on that there? So let's take a look at this one here together. What is the volume of CO2 that would be produced in this case at 37 degrees Celsius, 1 atmosphere, if we started with 5 grams, 5.6 grams of our glucose? We basically want to know the volume of this gas, and since it's a gas, we'll take all the gas sort of information with it, like our temperature is 37 degrees Celsius, our pressure is 1 atmosphere. We always have R again available to us, even though it's not given to us in a problem. And like normal, we're going to convert that into Kelvin. So we'll take 37 plus 273. So if we think about what is going on here in terms of our ideal gas law for CO2, we definitely have pressure. We do have temperature. We do have R. And we do have, that's about it. We're looking for volume in this case. So that's all we have. So you can see the one thing that we're actually missing to get to volume is actually moles of the CO2. And that's really where the stoichiometry comes into play. We're going to use our grams here of the C6H12O6. And we're just going to use stoichiometry like normal to figure out how many moles of CO2 we would produce. Once we have that, we then have everything we need for the ideal gas law. So before we can do that, we got to do a little molar mass of C6H12O6. That's going to be 6 times our 12.01 for our carbons, plus 12 times our 1.008 for our hydrogens, plus 6 times 16 for our oxygens. That's going to get us here 6 times 12.01 plus 12 times 1.008 plus 6 times 16, 180.2, it looks like. So we have an equation that's balanced. We're then going to convert what they gave us into moles. So we'll take our 5.6 grams of C6H12O6. Use the molar mass here, 180.2 grams per mole. That's going to get rid of our grams. This would give us moles of our C6H12O6, but remember, we're really looking for CO2. So this is where the stoichiometry is going to come into play. We could get an answer, just continue on with the calculation. So I'm just going to continue on. And from the equation, we see that for every 1 mole of the C6H12O6 we put in there, we get 6 moles of CO2. And once again, that is the mole-to-mole relationship between those two guys from the balance equation. That's going to get us 5.6 times 6 divided by 180.2, 0.18646 moles of CO2. So now we do have the moles of CO2 from the stoichiometry. And we have everything we need to solve for V. V in this case would equal nRT over P. We'll take all of our information here from the gas and we'll put it in there. So V would equal Rn, which is 0.18646. Definitely gonna run out of room there. Let me try maybe a different spot, I think. The page, I think. So we'll go with V is equal to nRT over P. So our N there is 0.1864 moles, I believe. Our 0.08206, which is our R. Our temperature there was 310. And our pressure was, where'd it go there? 1 atmosphere, not too bad. 1 atmosphere. Atmospheres cancel, Kelvin cancel, moles cancel. Gonna leave us volume. And here that would be that times 0.0206 times 310, about 4.74 liters of CO2. By the way, that would be a theoretical yield, as that is a product and how much volume we would actually produce in this case. Yeah. So really kind of the same 4 steps, except as you can see here, we're going to use the ideal gas law at the end rather than just moles to grams. Any questions on that one there? All right, one last one here, I think. Calculate the volume of hydrogen gas produced at STP if you started with 5 grams of magnesium and excess HCl. So see what you come up with. Magnesium 2431. Follow those 4 steps. Use a gas law probably somewhere along the way there. Be good. Okay, so let's take a look since we're getting to the end here. We want to calculate the volume of hydrogen gas, which is over here. So we're looking for the volume. We are producing it at STP, which means the temperature is 273 Kelvin. The pressure is 1 atmosphere, as that is what STP stands for. Might as well throw it in there. We always have R, 0.08206. Here's out of Kelvin mole. So if we just think about sort of the ideal gas law here for H2, we again have R, we do have T, we do have P, and again, we're looking for the volume. We are once again missing the moles for the H2, and that is where the 5 grams of magnesium is going to come into play. we're going to use stoichiometry to get to how many moles of hydrogen we produced. So we have a balanced equation. We're going to take what they gave us and convert it into moles. So 5 grams of magnesium, molar mass from the periodic table, 2431 grams per mole magnesium. Again, going to do the mole to mole relationship between those two, which looks like a 1-to-1. So that's not too bad. So 1 mole of magnesium will give me 1 mole of hydrogen. And again, this is like step 2 and then step 3. Moles of magnesium going to cancel, going to leave us moles of hydrogen. And that will get us 5 divided by 2431. And that is it, I think, divided by 1, basically. 0.205, 68 moles of hydrogen. Now we do have the moles of hydrogen. That would be a theoretical yield there. We'll solve for V, nRT divided by P. Putting in our numbers, 0.20568 moles of hydrogen. Our R, 0.8206 liters atmosphere Kelvin mole. Our temperature of 273 Kelvin. And our standard pressure there of 1 atmosphere. Moles cancel, Kelvin cancel, atmospheres cancel, leaves us liters here, and that will get us 0.08206 times 273. Looks like about a 4.61 liters of H2 in this particular case. So again, that would be kind of like step number 4. First off, any questions on that there? Now, once again, if you remembered, this again is at STP, which means you could have used that relationship we saw earlier. 22.414 liters is 1 mole at STP. So you could have just picked up from the moles of your H2. And again, you could have just used that without the ideal gas law. Those would cancel, and that also should get you up there as well. So again, you can shortcut the ideal gas law if you're at STP conditions, but once again, as I mentioned earlier,